I hope everybody can see the screen.
Yes, sir.
Okay. So, in the last class, we discussed about different types of supports, different types of beams, different types of loads. Now, in different types of loads, we came across point load, uniformly distributed load, uniformly varying load. Uniformly varying load. Now, before moving ahead, first let us understand how do you convert this uniformly distributed load and uniformly varying load to a point load. So it is very important that any type of loading given, you are supposed to convert it to a point load. It might be either a horizontal load or it might be a vertical load, because we use equation of equilibrium wherein we sum up all the horizontal forces and we sum up all the vertical forces. Yes. Now, in this class, we are going to learn how we are going to convert the UDL and UVL to point load and where are we going to locate that point load. So two things are very important in this. The first thing is conversion to point load, and the second is location of that point load. So two things are to be understood very clearly. Now I have given here UDL. UDL is nothing but it is uniformly distributed load, whereas UVL is uniformly varying load. Now first let us see how do we convert these loads to a point load. Point load. Now the first thing, UDL. Conversion of UDL to point load is nothing but it is area of rectangle. And UVL is area of triangle. The reason for conversion of these two loads being area of rectangle and triangle is because we denote them in the form of rectangle and triangle. So we can see here UDL denotion. How is it done? It is either done in the form of road humps, or it is in the form of a rectangle. It is in the form of rectangle. Whereas UVL, we denote it in the form of triangle. So either this type or in this type. So the first type, we see that it is gradually decreasing and it becomes 0. Whereas in the second, it gradually increases and reaches the maximum. Now, in this UVL, since the loading is represented in the form of a triangle, we need to understand the components of the triangle. We need to understand the components of the triangle. Now, you can see that in triangle, they are given with apex and base. What is apex? Apex is the pointed edge of the triangle. So you can see the pointed edge of these triangles is called as apex, whereas the other end is called as base. Other end is called as base. Or you can easily remember this by taking an example of your feet. So if you take an example of your feet, the toe represents the apex, whereas the other end represents the base. Other end represents the base. So these two terms in triangle are very important so as to understand the location of point load. Location of point load. So UDL is nothing but conversion is area of triangle rectangle, whereas UVL is area of triangle. So this is how you convert UDL and UVL to a point load. Now next, let us come to the location. Now once I convert the UVL or UDL to point load, where should I place them? Where should I place them? So in case of UDL, the point load will always act at the CG of rectangle. CG of rectangle, that is center of rectangle. Center of the rectangle or center of the span, what you can call. Whereas UVL, it lies in the CG of the triangle. CG of the triangle. CG of the triangle in the sense it is either 2/3 from apex, means if you measure it from apex, it will be 2/3 of total length. If you measure it from base, it will be 1/3 of total length. 1/3 of total length. I repeat, CG of triangle, it lies at a distance 2/3 of total length when measured from apex, or it will lie at a distance of 1/3 of total length when measured from base. Now you will understand this once I show you a simple example wherein we are learning to convert the UDL or UVL to the point load. Now, as you can see here, the next page, it is conversion of UDL to a point load. UDL to point load. So you can see a UDL of intensity 10 kilonewton per meter. I repeat, whenever UDL or UVL is given to you, you should be very, very careful with the magnitude unit. You should see what is the unit which is being given in the question. So you can see that in this question, the UDL unit is 10 kilonewton per meter. It is acting over a span of 6 meters. So 10 kilonewton per meter acting on a span of 6 meters. So 1 meter, 10 kilonewton, 6 meter, how much? It is nothing but simple. That is conversion. How do you convert this UDL to a point load? We have discussed in the previous page that it is area of rectangle. That is simple, 10 into 6. So when you multiply this 10 into 6, you will get a magnitude of point load as 60 kilonewton. 60 kilonewton. Where will it act? It will act exactly at the center. In the sense, since it is 6 meter, it will act center in the sense 3 meter on either side. 3 meter on either side. So this is how you convert a UDL to a point load, and where will it act? It will act exactly at the center, that is CG of rectangle. Now I've taken one more example here. A lot of difference between both. You see in the first example, what is the unit given? The unit given is 10 kilonewton per meter. Whereas in the second example, the unit is 100 kilonewton. Lot of difference between this and this. I'll tell you why. Now see, only in case the unit is kilonewton per meter, then only you are going to calculate area of rectangle and write the magnitude of point load. In case if it is not kilonewton per meter and if it is only kilonewton, it means that 100 kilonewton itself is the point load. So you can see here 100 kilonewton, I have shown it directly as a point load, and location as usual, it will be the same. It will be at the center. The span of this beam is 4 meters. Span of this beam is 4 meter, and it is going to act exactly at the center, that is 2 meters on either side. So in both these examples, I hope you have understood the difference. If it is 10 kilonewton or if it is kilonewton per meter, then only you are going to convert it by calculating the area of rectangle. If the unit is only kilonewton, you are going to directly show it as a point load with the same magnitude. Only thing is you have to take care about the location. So this is how you are going to convert the UDL to the point load. Now next, let us come to conversion of UVL, that is uniformly varying load, to a point load. Now you can see this UVL is represented in the form of a triangle. Now you can see that the base of this triangle, or the length of the base, is 9 meters. It is spreading over 9 meters. Okay, and as we all know that The pointed edge of the triangle is apex, whereas the base is the other end. So other end is base. What is the intensity? Intensity of this UVL is 4 kilonewton per meter. 4 kilonewton per meter, which means that this higher end edge is subjected to a loading of 4 kilonewton per meter. It gradually decreases, and to the other end it becomes 0, thereby forming a triangle. Now first let us understand how do you convert this UVL to a point load. So we have discussed that conversion is nothing but it is area of triangle. And what is area of triangle? It is half base into height. Half base into height. So it is half into base. How much is base? 9 meters. Height is 4 kilonewton per meter, or it is 4. So 2 ones are 2 twos are. Intensity becomes 18 kilonewton. So you have a 18 kilonewton point load after conversion. Now the next question arises, where will it act? Where will it act? We know that always the CG of triangle is 2/3 of the total length when measured from apex, or it is 1/3 of the total length when measured from base. I repeat, if you are measuring the distance from apex, it will be 2/3 or 2/3 of total length. If you are measuring it from base, it will be 1/3 of total base. Okay, now let us see the calculation for this. We know that the length of the base is 9 meters, and we have got the intensity of point load as 18 kilonewton. So the location of this point load is, if I am measuring it from apex, so it will be 2/3 of total length. So it will be 2/3 of 9. So 3 ones are 3 threes are 2 threes are 6 meters. So this point load will act at a distance of 6 meters from apex. Or if I am calculating it from the base, so it will be 1/3 of the total length. So total length is 9 meter. 1/3 of 9. 1/3 of 9. 3 ones are 3 threes are. So it is nothing but 3 meters. So if you are measuring from base, it will be 3 meters. Or if you are measuring from apex, it will be 6 meters. Both put together will give you the base length as 9 meter as well. So you have to always keep one thing in mind when you're converting UVL. If you are measuring the distance from apex, it will be 2/3 of the base length. If you are measuring it from the base, it will be 1/3 of the base length. 1/3 of the base length. So be very careful when you are calculating the location of point load, especially in UVL. Okay, now the next part what we are going to study is something called as trapezoidal type of load. So we are done with UDL, which resembles a rectangle. We are done with UVL, which resembles a triangle. Now let us come to trapezoid load. Now, as in case of UVL and UDL, here also it is same. What is same? It is nothing but how do you convert. So here also conversion and location is very, very important. Now see, if you can see this diagram, there is a trapezoidal type of loading. The base length is 6 meters. The higher end of the edge has an intensity of 10 kilonewton per meter, whereas the other end has 4 kilonewton per meter. Now I need to convert this trapezoid type of load to a point load. Now for that, what I do is, this trapezoidal load, I will first convert this into, or I will I will split it into two diagrams. I hope everybody can see this dotted line which I have drawn in red ink.
Yes,
That
sir.
is, yes. that is here. If I draw a straight line here, this trapezoid is being distributed among a triangle and a rectangle. That is, it is UVL plus UDL. UVL plus UDL. Now, once you split it into UVL and UDL, you are supposed to write the intensity of loading. For trapezoidal load, it was 10 kilonewton per meter on one end, and it was 4 kilonewton per meter on the other end. Now, when I split it, so I'll just take out this triangle upper portion and I'll keep it here. So I know that this end, right end, is a apex, which is a pointed end. So this will be apex, and the other end is the base. But what is the intensity of this base? This 10 kilonewton per meter is this total length, total vertical length. But I require only the length of the triangle. So the length which actually supports the triangle, and that length is only up to here, So I want only this length. So how do I get this length? Total is 10 kilonewton per meter, and this base, that is 4 kilonewton per meter. I'll deduct this 4 and I will get the length as 6 kilonewton per meter. So basically I have a triangle, or I have a UVL of intensity 6 kilonewton per meter, which is spread over a span of 6 meter. Okay. Now next, let us come to the UDL now. So first portion, top portion is over. Let us concentrate on the bottom portion now. So you have a UDL, So a simple rectangle here. So this rectangle is of intensity 4 kilonewton meter only, which you are going to show here. So you have split this trapezoid into a triangle, that is UVL of intensity 6 kilonewton per meter and a UDL of 4 kilonewton per meter. Now what do? I will convert this UVL and I'll keep a point load. I'll convert this UDL and I'll keep a point load. So basically I'm going to have 2 point loads on the diagram, one of UVL, one of UDL. Okay. Now let us come to UVL first. Now, how do we convert UVL to point load? Area of triangle. So see here, area of triangle I have calculated. It is half base into height, where base is 6 meters. And the height is also 6 meters. So half into 6 into 6, when you cancel it, you are going to get it as 18 kilonewton. Now since this end is base and this is apex, I have told you the location is 1/3 when measured from base, or 2/3 when measured from apex. So next is about the location. So if you can see the location of this point load, if I measure it from the apex, here, it will be 2/3. So 2/3 of what? Total length, base length. 2/3 of 6. So 2/3 of 6, which is 4 meters. So this point load of UVL is going to act at a distance of 4 meters from apex. Or it is going to act at 1/3 of 6 from base. So 1/3 of 6 is nothing but 2 meters. So the location of this point load of UVL is 4 meters from apex or 2 meters from base. So now I have successfully converted UVL to point load. Now next, let us come down to this UDL. We all know how do you convert the UDL to point load. That is simple, area of rectangle. So it is 4 into 6. Why 6? It is the base length. So 4 into 6, which is 24. And where is it going to act? It is going to act exactly at the center. That is, since it is 6 meters, it will be 3 meters on either side. It will be 3 meters. The first thing is, let us understand what are the points to be remembered when we are solving problems on equilibrium of coplanar concurrent force system. Now, the first thing is, we need to understand that in coplanar non-concurrent force system, we use all the three conditions of equilibrium, or we use all the three equations of equilibrium. That is sigma fx, sigma fy, and sigma moment. Sigma moment. Okay. Now, in case of concurrent force system, we apply only two equations, that is sigma fx and sigma fy, which you have already done and you have solved the problems on the same. The next point is, you will draw the free body diagram of each beam which is given to you. So basically, in this non-concurrent force system, we are going to solve problems on beams. We are going to solve problems on beams, and you are going to draw the free body diagram of that beam. Now, I hope everybody remembers what does free body diagram consists of. It consists of three things, that is self-weight, action, and reaction. But in this case, the first term, that is self-weight, we are going to neglect it. That is, self-weight of the beam here is neglected, but we are going to represent the action and reactions. Actions in the sense, all the forces which are actually acting on the beam, those are called as actions. Now, those actions, if they are not in the form of horizontal or vertical or movement, we are going to convert it. In the case, for example, if you have a UDL given in the beam, you're supposed to convert it to point load. If you have an inclined load which is acting on the beam, you're supposed to convert it to horizontal component and vertical component. So basically, your free body diagram should have all the actions in the form of either horizontal force, vertical force, or movement. Not any other force other than these. Any other force, your first thing is to convert them. So this was all about actions. Next is coming to reactions. Where are reactions formed? Reactions here are formed in the place of supports. In the place of supports. So all the supports are to be replaced by reactions. Replaced by reactions. Yes. So the free body diagram mainly consists of actions and reactions. The next is, apply these three conditions of equilibrium in order to calculate the unknown reactions at the supports. Means you are supposed to apply these equations to calculate the unknowns. Calculate the unknowns. Unknowns are nothing but reactions. Now let us just recall how many reactions will be there for each type of supports. For each type of supports, we have already studied types of supports. We know that there are three types of supports. One is a roller support, the other one is a hinge support, and the third one is fixed support. Now, roller support, if there is a roller support, the roller support will have only one vertical reaction. Only one vertical reaction. Now that vertical reaction, it might be either upwards or it might be downwards. It all depends on how is the action. How is the action? If the action is acting downwards, then obviously the reaction will be upwards. So action and reaction will be opposite to each other. So roller support has only one vertical reaction. Hinge support has two reactions. That is, one horizontal reaction and the other one is vertical reaction. That is hinge support. And the third one is a fixed support. And this fixed support, it has horizontal reaction, it has vertical reaction, and it also has a movement. it also has a movement. Now when I say horizontal reaction, that horizontal reaction might be either rightwards or it might be leftwards. Again, it is dependent on the type of action. If the action is in the rightwards, the reaction will be in the leftwards. If the action is in the leftwards, then the reaction will be in the rightwards. Similarly, vertical reaction again might be upwards, might be downwards, depends on the nature of action. And movement, the third one is movement. What type of movement? It might be either clockwise movement or it might be anti-clockwise movement. Again, it is based on the type of movement which is actually causing in the beam. In the sense, in case due to application of load, if it is observed that the beam is rotating in a clockwise direction due to application of load, then a resisting anti-clockwise movement is to be provided in order to keep that beam in equilibrium. So basically we are calculating reactions here so that the beam is in equilibrium. It will not change its position. So if the beam is moving in a clockwise rotation due to action of forces, the reaction will be anti-clockwise movement. And if the beam is moving in the anti-clockwise direction due to application of forces, then the movement will be clockwise. Movement will be clockwise. So these are few of the points which are to be remembered before starting with the problems. Before starting